This question is about aromatic carboxylic acids and their derivatives. Part A. The flowchart below shows some reactions of compound H. In the boxes, draw the organic products of these reactions. So let's start with the top left product. So we're reacting with a carbonate, and carbonates react with acid. So we look at the acid group of compound H, which is our carboxylic acid. And what a carbonate does is it turns the carboxylic acid into a salt. So we're going to have a carbon, a double bond oxygen, an O negative, and Na plus. The Na plus coming from our sodium carbonate reagent. And then we have our OH remaining the same. So this is our top left product. So then if we look at NaOH, which is our top right product, this is going to react with the OH group and the carboxylic acid group. So if we circle these on compound H, here we have our carboxylic acid and our OH group. So what's going to happen is similar to the top left, where we have our carboxylic acid turning into our O minus Na plus, so our salt. And then the same thing's going to happen to the oxygen. We're going to have an O minus and an Na plus. And we keep our ring the same. So then finally, our bottom product, we're reacting with bromine, and this is going to be what's called an electrophilic substitution on the benzene ring. So what's going to happen is it's going to substitute next to the OH. So we're going to have our ring the same, our carboxylic acid group the same, our OH group the same, and then next door to it we're going to have a bromine that's substituted onto the ring. To get the 3 marks for this question, you get a mark for each correct product. Part B. Compound H is used in the synthesis of polymer I, as shown in the flowchart below. Complete the flowchart by drawing the structure of the acyl chloride and 2 repeat units of the polymer I, and stating the formula of the reagents required for this first stage on the dotted line. Let's start by drawing our acyl chloride. So an acyl chloride is a carbonyl group, so we're going to have our C double bond O, but instead of the OH in the carboxylic acid, we have a chlorine. But the rest of the compound stays the same. The reagents for turning a carboxylic acid into an acyl chloride are SOCl2. So it's just one reagent here. And now we're asked to draw 2 repeat units of polymer I. So polymer I is when you're having the acyl chlorides reacting together. So this is a similar process to when you have a carboxylic acid and an alcohol, where you produce a polyester and water. But instead of producing the water, we're going to produce hydrochloric acid, because we're going to have our hydrogen and our chlorine rather than having our hydrogen and our OH. So the ester is the same, it's just the byproduct that's different. So we're going to have our 2 repeat units, so our rings connected to our ester functional group, and then another ring, and just to show that it's an ester, we're going to have a C double bond O, then a dotted line, and an oxygen with a dotted line. And then make sure we show that they're rings by drawing the circles. In this question, you get a mark for the correct reagent, a mark for the correct acyl chloride group drawn. You get a mark for having an ester link in your polymer, and then you get a mark for having the rest of the structure correct. Part C. A cosmetic product containing 4 esters J, K, L, and M is analysed by gas chromatography and mass spectrometry. The results are shown below. The number of peaks are the relative molar proportions of the compounds in the mixture. Part 1. The concentration of ester K in the cosmetic product is 9.13 times 10 to the negative 2 grams per decimeter cubed. Using the results, calculate the concentration in moles per decimeter cubed of ester M in the cosmetic product. Give your answer to two significant figures. So the first key bit of information in this question is that we're given the concentration of ester K, which is 9.13 times 10 to the negative 2 grams per decimeter cubed. So if we use the mz of K, we can work out the concentration in moles per decimeter cubed, because that's what we want our final answer in. But we do want it of M and not K, so this is just something to be wary of in the later bit of the question. So if we divide 9.13 times 10 to the negative 2 by 166, we get 5.5 times 10 to the negative 4 moles per decimeter cubed. And this is because if we have grams per decimeter cubed divided by grams per mole, because this is what mz is measured in, we cancel out our grams and we end up getting moles per decimeter cubed. So here we've got the concentration of K, and we eventually want the concentration of M. So if we look at the areas, we've got M is 5.9 and then K is 4.3. So what we can do is we can take 5.5 times 10 to the negative 4 and multiply this by the proportion. So we can do 5.9 divided by 4.3, and that equals 7.5 times 10 to the negative 4 moles per decimeter cubed. And we want our answer to two significant figures, which it is at the moment, so that's great. So we can put 7.5 times 10 to the negative 4 as our final answer. In this question, you get a mark for the concentration of K, so 5.5 times 10 to the negative 4, and a mark for the concentration of M, so 7.5 times 10 to the negative 4. Part 2. A general structure for esters J, L, and M is shown below, where R is an alkyl group. Use the mass spectrometry results to deduce possible structures for esters J, L, and M. So here I've just drawn the general structures, but leaving out the R groups. We're told in the question that the R group is an alkyl group, so it's made up of carbon and hydrogen. So we can start by working out the relative formula mass, or the MZ, of the general structure. So that's going to be 1 for our hydrogen, plus 16, so that's our OH, plus our ring of 6 carbons, so that's 12 times 6, plus 4 hydrogens, plus a carbon, and then plus 2 oxygens. And that equals 137. So if we look at the MZ values for J, L, and M, so we have J, L, and M, we can work out the relative formula mass of our R groups. So that's going to be minus 137, that equals 15. Then minus 137, minus 137, we have 43. So using this information, we can work out what our R groups are. The first one we can start with is J, so 15, that's going to be CH3, because carbon has a relative formula mass of 12, 12 plus 3 is 15. So L and M are going to have the same R group value in terms of their relative formula mass. So you can put them either way round because there's no way of knowing which one's which based on the information that we're given. So if we work out how many carbons are present, we do 43 divided by 12, and that equals about 3.6. And you can't have 0.6 of a carbon, so we're going to have 3 carbons. So we do 12 times 3, and this equals 36. So we need to do 43 minus 36, and that equals 7. So we're going to have 7 hydrogens present. So we can have just a long group chain, so we can have CH2, CH2, CH3. This is going to give us 7 hydrogens and 3 carbons, so it equals 43. Or we can have CH and then CH3 brackets 2. This also gives us 7 hydrogens and 3 carbons. To get the 3 marks for this question, you get a mark for each correct structure for the esters. You can have L and M the other way round though.